Myself Dr. W. Vidyanare from Kamlani Mahavidyalaya, Nagpur. Today I am going to discuss the shapes of different orbital, s-orbital, p-orbital, d-orbitals, and after that three important principles. One is a Aufbau Principle, second is a Pauli Exclusion Principle, and third one is a Hund's maximum multiplicity. So, and these rules are used to write electronic configuration of the element. So today we are going to discuss the atomic structure and in which the shapes of the different orbitals. So here the outline of the discussion here is the shapes of orbital, s orbital, p orbital, d orbitals, and after that Aufbau principle, after that Pauli principle, after that Hund's rule of maximum multiplicity, and then electronic configuration of the element, first row, second row, third row, and fourth row. After that the electronic configuration of positive and negative ions. So first part is now shapes of s orbital. As we know, this is the shape of one s orbital, this is the shape of two s orbital, and s orbitals are non-directional, spherically symmetrical. It means that the electron density is same at particular distance from the nucleus. And here in this figure 1, that x, y and z, three axes are there, but the shape electron density or electron dot structure is shown here in a spherical manner, not along the any axis, and therefore here we can say that s orbital, this is the shape of one s orbital, and similarly the shape of two s orbital is there. Here this is one electron density sphere, second this is the space, but here between these two there is a space, that is a region without dot, that is known as the node or nodal surface. Here the electron density is actually the node is that where the probability of finding the electron is 0. So the important difference between these two is that 2s orbital is larger in size as compared to 1s, and there is a node in 2s as compared to 1s. So again we can say that s orbitals are non-directional and spherically symmetrical. This means that the probability of finding the electron is same in all direction at particular distance from the nucleus. 1s orbital is shown in the first figure, 2s orbital is shown in a second figure, and important feature of 2s orbital is that it is also non-directional, spherically symmetrical, but there is a node or nodal surface, that is the region without dot where the probability of finding the electron is 0, and therefore this space is known as node or nodal surface. The important point is that 2s orbital differ from 1s orbital in that it is larger in size and having a nodal surface, and all other higher s orbitals have the similar shape. So the shape of s orbital is a spherical shape. So shape of the s orbital is spherical shape. So the shape of 1s and shape of 2s orbital. So all s orbitals have spherically symmetrical shape. Second one is a shape of p orbital. Now in case of p orbital, here I have shown for p orbital, L means azimuthal quantum number, L value is 1, and therefore magnetic quantum number values are -1, 0, +1, and which this three value of m indicate there are 3 p orbital in p subshell. So these 3 p orbitals are one is a px orbital, py orbital, pz orbital. So px, py and pz, and each p orbital consists of two lobes. These two lobes are present along the x-axis, then it is known as px. When the lobes are present along the y-axis, it is known as py. When the lobes are present along the z-axis, it is known as pz. So here the shape of p orbital is dumbbell shape, just looking like a dumbbell. Therefore the shape of this p orbital is dumbbell in shape. So again now repeating that for p orbital, L value azimuthal quantum number is equals to 1. Therefore there are three possible orientation corresponding to the value of m. So value of m is -1, 0, +1. This means that there are 3 p orbitals in each p subshell. These p orbitals are denoted as px, py, pz. These three orbitals are equal in energy, and therefore they differ only in the orientation. And here each p orbital consists of two lobes of high electron density present along the x-axis, y-axis or z-axis, and therefore depending upon the lobes present on the x-axis, they are known as px, py, pz. In case of second shell, so here 2px, 2py, 2pz. So these, and the shape of the p-orbital is dumbbell shape. So shape of s-orbital is spherically symmetrical, spherical shape, and shape of p-orbital is dumbbell shape, look like a dumbbell, and therefore the shape is known as a dumbbell shape. So p orbitals are dumbbell in shape. And next one is now d-orbital. D-orbitals are 5 types: dxy, dyj, dxz, d square, y square, dz square. For d-orbital, L equals to 2. Therefore, the value of magnetic quantity number m equals to -2, -1, 0, +1, +2. It means that there are 5 d orbital in d subshell, and these 5 d orbitals are shown here: dxy, dyj, dxz, d square, y square, dz square. All the 5 d orbitals are equal in energy, but they differ in their orientations. So the shape of this orbital also we can say that double dumbbell shape. And now first 3 orbital, 1, 2, 3, means dxy, dyj, dxz. These 3 orbitals are equal because lobes are present between the axes. When the lobes are present between x and y, it is known as dxy. When lobes are present between the y and z, it is known as dyz. When lobes are present between x and z axis, therefore it is known as dxz. So first 3 orbitals are equal. Each orbital first 3 orbital, in case of first 3 orbital, each orbital consists of 4 lobes, and the lobes are present between the axes, and depending upon the axis they are known as dxy, dyj, dxz. However, now in case of other 2 orbitals, that is d square, y square and dz square. In case of d square, y square, this orbital also consists of 4 lobes, but the lobes are present along the axis, particular axis x and y, and it is noted that this orbital is exactly like dxy orbital, except that it is rotated through 45 degree around the z axis. And third one, last one is a dz square orbital. This orbital consists of 2 lobes of high electron density, and these lobes are present along the z axis, and therefore the shape of here there is also one important point, is that there is a ring of high electron density at the center of this orbital. So the first 3 orbitals are equal and last 2 orbitals are equal, and in case of these 3 orbital, lobes are present between the axis. In case of these 2 orbital, the lobes are present along the axis. So there are 5 d orbital, and all the 5 d orbitals are equal, only they differ in their orientations. So shape may be considered as double dumbbell or having a complicated shape. So the shape of s orbital is spherical, shape of p orbital is dumbbell shape, and shape of d orbital is complicated or double dumbbell shape. Next, now we are going to see the important principle, and 3 principles are there. One is a Aufbau principle, second is a Pauli exclusion principle, third is a Hund's rule of maximum multiplicity. All the 3 rules are used to write electronic configuration of the element. So now first principle is Aufbau principle. Aufbau means building up, and now here what is the statement of this Aufbau principle? The principle of the Aufbau principle state that in the ground state of an atom, electron enter the lowest energy orbital first, and then subsequently higher energy orbitals are filled. It means that electron first go to the orbital which have lower energy, and then subsequently higher energy orbitals are filled. Again repeating, what is the statement? According to this principle, the principle is that in the ground state of an atom, electron enter the lowest energy orbital first, and subsequently higher energy orbitals are filled. It means that the electron first go to the orbital which is having lower energy, and subsequently higher energy orbitals are filled. So the sequence is here now. Here is shown also the order of filling the orbitals. Electron first go to the 1s, after that 2s, then 2p, then 3s, 3p, 4s, 3d, 4p. So here 4s filled first, after that 3d. So this is the sequence of filling the atomic orbital. And here another diagram shows the sequence of filling the atomic orbital. So electron first go to the 1s, after that electron go to the 2s, after that electron go to the 2p, 3s. This is shown the sequence 3p, and after 3p 4s, after 4s then 3d. So 4s come first and then 3d. It depends upon the energy. So energy of lowest energy orbital field first and subsequently higher energy orbitals are filled. So this is the sequence of filling the atomic orbital. So the Aufbau principle says that electron enter the lowest energy orbital first and subsequently higher energy orbitals are filled, and this is the sequence of filling the atomic orbital. So this is the important rule which show the sequence of filling atomic orbital, which is used to write electronic configuration of the element. Second rule is that Pauli exclusion principle, and in case of this is an important principle which limits the accommodation of electron in an orbital, and this principle was proposed by Pauli in 1952, and this principle states that no two electron can have same values for all the four quantum number. The statement is that no two electron can have same values for all the four quantum number. So it means that there are four quantum number. According to this principle, three quantum number value first, second, third may be same, but fourth quantum number, spin quantum number must be different. So again repeating what is the statement. According to this principle, it states that no two electron can have same values for all the four quantum number. In orbital, each orbital can have maximum 2 electron, and if there are 2 electrons, they should have opposite spin. So this is the important principle which limits the accommodation of electron in an orbital, and this was given by the Pauli, and therefore it is known as Pauli exclusion principle. An important statement of this principle is that no two electron in an atom can have same values for all the four quantum numbers. Now here in this case I can say that now here orbital can have maximum 2 electrons. Why there are 2 maximum electrons? So we can say that here electron having the same values for n and l and m are said to belong to the same orbital. For example, consider the K shape, that is n equals to 1. The electron will have only one values, l equals to 0, and one value of m, that is m equal to 0, but it can have two values of spin quantum number s, either plus 1 by 2 or minus 1 by 2. This means that although n, l and m are the same for the 2 electrons, but their spin quantum number are different. So it is shown here in the next slide. So here it is shown that for K shell, for example, K shell contains 2 electrons, and if there are 2 electrons, they should have opposite spin in the orbital. So for n, l, m, n is 1, l is 0, m is also 0, but s is equals to plus 1 by 2. And for second electron, n equals to 1, 0, again 0, and minus 1 by 2. So first 3 quantum number value may be same, but both the fourth quantum number value must be different. So this is the statement of Pauli exclusion principle. No two electron can have same values for all the four quantum number. Now here, so it is clear from this here, and now this, therefore this principle give the limitation of the accommodation of electron in an orbital. So each orbital can contain maximum 2 electron. So this is given by Pauli exclusion principle. An orbital can contain maximum 2 electrons, and if there are 2 electrons in the orbital, they should have opposite spin. As we know that s-orbital is only one type, therefore it contains 2 electrons. p-orbitals are 3 types, px, py, pz, therefore each orbital contains 2 electrons. So 3 orbital contains 6 electrons. So p subshell or p-orbital contains total 6 electrons. So in this way the orbitals are filled. Now here this table shows the distribution of electron. Now here value of n is 1, l is 0, m is 0, and s may be plus or minus 1 by 2. So orbital is 1 s orbital, and sub level it contains, s subshell contains 2 electrons. So this is the main energy level, that is main shell K shell contains 2 electrons. If there are 2, n value is 2, principal quantum number 0, 1, 2 values are there because s start from 0. So 0, 1, if it is 0, 0. When the s value is 1, then 3 values are there, minus 1, 0, plus 1, and for each there are plus or minus half value of spin quantum number. So in this case, when n is 2 and it is 0, then 2s. When 2 and 1 is here, then 2p. So 2s contains 2 electrons, 2p contains 6 electrons because each orbital have 2 electrons. These are the p3 types, and therefore p contains 6. So total 6 to total are the 8 electrons in the second shell. Similarly, here if the value of n is 3, 0, 1, 2, and these are the value when it is 0, 0, when it is 1, L minus 1, 0 plus 1, when 2, minus 2, minus 1, 0 plus 1 plus 2. And this is the spin quantum value. So 3s subshell, 3p, 3d. 2, p contains 6 and d contains 10. So total are 18 in the third main shells. So this is the distribution of electron in the subshell and orbital, subshell and main shells. So Pauli exclusion principle says that no two electron can have same values for all the 4 quantum number, and according to this principle it give an accommodation of electron in an orbital. So there is a limitations, and we can say that an orbital can contain maximum 2 electron. This is given by Pauli. An orbital contain maximum 2 electron in an orbital. Maximum 2 electrons are there, and if the orbital have 2 electrons, they should have opposite spin. So this is the second principle. First principle was Aufbau principle, show the sequence of filling the atomic orbital. Second Pauli exclusion principle shows that an orbital can contain maximum 2 electrons. And third one is there, Hund's rule of maximum multiplicity, and the statement of this we should have to know the statement and remember the statement. So what is the statement of Hund's rule? According to this rule, electron pairing will not take place until all the available orbital filled singly with the parallel spin. Again I am repeating that the statement is very important. According to this rule, electron pairing of electron will not take place until all the available orbital filled singly with the same spin or parallel spin. For example, now we can take here carbon. It means that what is the meaning of statement? Orbital contains 2 electron, 3 electron, but pairing will not take place. For example, p-orbital. P-orbitals are 3 types. So if the p-orbital contains 3 electron, they cannot be 2 electron in one orbital and singly on the other. So this is not according to the rule. So the rule says that available orbital means 3 orbitals are there, then 1, 1, 1 can fill singly, and then pairing will take place. First pairing will not take place. So according to the Hund's rule, the pairing of electron will not take place until all the available orbital filled singly with the parallel spin. So we can take the example of carbon. We can take also the nitrogen, oxygen. So carbon having the atom number 6, electron configuration 1s2 2s2 p2. So now there 2p have 2 electrons. So in the next slide now here 2p have 2 electrons. So this is 2p orbital. P orbitals are 3 types, 1, 2, 3. 2p and there are A, B, C, 3 types of distribution of electron is given. So here this 2p contains 2 electrons. We can show the 2 electron in p subshell in a p orbital in this way. 2 electrons are here in one. 2 electrons are here separately but opposite spin. Here 2 electrons are filled. So these 3 are the different cases. So according to the Hund's rule, which one is correct? A, B or C? The C is the correct answer. C is the correct answer, because here pairing of electron take place, but according to the rule pairing will not take place because orbitals are available. In case of this, 2 electrons are in a separate orbital, but this is not according to the rule, because the electron go to the orbital with the same spin, but spin is now here opposite. This is according to the rule. Pairing will not take place, but until the available orbital singly filled with the same spin. So this is correct. So in this way we can show another example of nitrogen. Nitrogen contains 2p3, oxygen contains 2p4. So as per the rule we have to write or distribute the electron here. So this is one example of carbon. So Hund's rule says that electron pairing will not take place until all the available orbital filled singly with the parallel spin. So in this way, these are the 3 rules of Aufbau principle, Pauli exclusion principle and Hund's rule, which are used to write electronic configuration of the element. Now by using all these 3 rules, we can write the electronic configuration of the elements. Now here, how to write electronic configuration? Suppose now here, this is the one example is shown here. This is the subshell. These are the number of electrons, and this number indicates the principal energy level. Principal means principal quantum number 1, 2, 3, 4 like that, and it is principal energy level. So in this way we have to write the configuration in terms of this. So first row of the periodic table contains 2 elements, one is hydrogen and helium. atom number of hydrogen, Z is the atom number equals to 1, helium having atom number 2. So configuration we can write 1s1, 1s2. So we can also show in this way also. So configuration of hydrogen, helium, 1s1, 1s2. This is the first row, contains two element. So the electronic configuration of now second row element. Now here the second row element contains 8 elements, and 8 elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and atom numbers are from 3, 4, 5, 6, 7, 8, 9, 10, and their corresponding electronic configuration is here 1s2, 2s1. Atom number is 3 means 1s contain 2 electron, and third one is goes to the 2s, because Aufbau principle says that after filling complete 1s, the electron go to the next orbital 2s, and s orbital contains maximum 2 electron, and in case of this atom number 4, 1s2, 2s2. So now here again 2s orbital is completely filled, so after next electron will go to the 2p orbital. So here in case of this configuration is 1s2, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So p orbital is filled progressively, and this is the electron configuration, and one by one electron, and this is the sequence, and configuration can also be shown in this way also in a box diagram. So here after that electron configuration of third row element, not ions, electron configuration of third row element, and again this contain 8 elements. 8 elements are sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Atom numbers are from 11, 12, 13, 14, 15, 16, 17, 18. And now in case of sodium, configuration is 1s2, 2s2, 2p6, because p contains 6 electrons, 3s1, and in case of this same 1s2, 2s2, 2p6, 3s2. This is completely filled. Now after this it will go to the electron will go to the 3p orbital. So again similarly 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. So in this way we can write the electronic configuration. So S contains 2 electrons, and P contains 6 electrons, D contains 10 electrons. So this is the configuration for third row element of the periodic table. Now electron configuration of fourth row element, not again ions here, fourth row element. So fourth row elements are potassium, calcium, and from scandium up to zinc is the first transition series element. So here in this case atom number is 19, 20 up to 30, atom number 30, and the configuration is shown here 1s2, 2s2, in this way 4s1, and here 4s2. Then electron will go after 4s, 3d1, 3d2, so d orbital filled progressively. To form scandium, the elements are d block. So here 3d1, 3d2. Again now the important point is that when last electron goes to the s orbital, it is known as s block element, and when last electron goes to the p orbital, p block. Here last electron goes to d orbital, therefore it is known as, all these elements are known as d block element. This is the first transition series from scandium to zinc, from atom number 21 to 13, and now this is here d orbital filled progressively, and here 1 by 1, 1, 2, 3, 4, 5, 6, 7, but not here. In case of chromium and in case of copper, they have exceptional configuration. In case of chromium, atom number is 24, here d1, d2, d3, here should be a d4, but now configuration is configuration should be here 4s2, 3d4, but now the configuration is 4s1, 3d5. Expected is different, actual configuration is 4s1, 3d5, and in case of copper 4s1, 3d10. So in case of these two elements, chromium and copper, they have this exceptional configuration, because the in case of chromium d orbital is half filled, in case of copper d orbital is completely filled. So half filled and completely filled orbitals are more stable, they have extra stability, and therefore they have this exceptional configuration. So chromium and copper have exceptional configuration because they have half filled and completely filled d orbitals, and half filled and completely filled orbitals are more stable because they have extra stability, and therefore this is the actual configuration of chromium and copper. So one by one d orbitals get filled. These are the configuration of fourth row element. Now also we can write the electronic configuration of ions. Ions are positive and negative, and now here it is also possible to write the in case of positive and negative ion. Now as we know that positive ion formed by the loss of electron, negative ion formed by the gain of electrons here. Now in case of this sodium ion, Sodium atomic number is 11 given, and now plus 1 means 1 electron is lost. So total number of electrons are here 10. So configuration is 1s2, 2s2, 2p6. And Mg2 plus. So magnesium atomic number 12. So 2 plus means 2 electron lost. So configuration is 1s2, 2s2, 2p6. In case of aluminum, atomic number is 13. So 3 plus 3 electron lost. So total number of electron 10. So configuration. All these three have similar configuration. In case of calcium 2 plus, atomic number is 20. So 2 plus means 18. So what is 2 electron lost out of 20? Then 18 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. In this way. In case of Cl, atomic number is 17. Minus 1 means 1 electron we have to add. So total number of electrons Cl minus 18. So configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Similarly, yes, atomic number is of sulfur is 14 plus here again now here we have to add 2 electrons. In the same way here we can write now in the oxygen atomic number is 8 and having the 2 minus means plus add the 2 electrons. So configuration is 1s2, 2s2, 2p6. Total number of electrons present in O2 minus is 10. So in this way we can also write electron configuration of cation or anion. So today we stop here, and we have discussed today the shapes of s-orbital, p-orbital, d-orbitals, and s-orbital are spherical shape, p-orbital have dumbbell shape, and d-orbital have double dumbbell or complicated shapes. And three important principles: Aufbau Principle, Pauli Exclusion Principle, and Hund's rule of maximum multiplicity. And all these three rules are we have used to write electronic configuration of the element. So again I am repeating is that Aufbau Principle used to it gives the sequence of filling the atomic orbital. Pauli Exclusion Principle shows that an orbital can contain maximum 2 electrons. And Hund's rule says that pairing will not take place until all the available orbitals filled singly with the same spin. So these are the important principle and configuration of first row, second row, third row and fourth row element.